Good evening and welcome. I'm Jay Asundi, the Executive Director at CSTEP,
Hello.
extending to all a warm welcome for today's discussion on the role of pumped hydro storage in the Indian grid. The team has put together a very knowledgeable and diverse group of panelists and discussants, where I'm sure we are to walk away from this meeting feeling truly informed. We have the pleasure of having Mr. Suni, currently advisor at POSOCO, Mr. Sumant Rao, former MD MESCOM and also advisor at CTEP, Mr. Pankaj Batra from IRADE, Manu Modgil from Shakti, Ms. Vibhuti Garg from the Institute for Energy Economics and Financial Analysis, and last but not the least, Mr. Agramu, who was with KPCL. I thank you all. I thank you all for contributing your time to this discussion. As you all know, India has set itself a really ambitious target of renewable energy, 450 gigawatts by 2030. Now, with the country bracing up to meet this ambitious target, and given the intermittent nature of renewable energy, energy storage systems are needed or almost necessary for what we need going forward. So among the various energy storage technologies that we have been examining for a while now, pumped hydro energy storage and battery storage are emerging as front runners. We also know that the Ministry of Power recently announced promotion of renewable energy and pumped hydro storage for decarbonizing the Indian grid. And we do also have anecdotal evidence that PHES or pumped hydro storage offers superior features, and yet we see that the growth of PHES in India has been not very good. It's been tepid so far. So this slow pace, we believe, can be attributed to the high cost associated with commissioning of these plants, the long gestation periods, and also the need to obtain environmental clearances, and then the low recovery of pricing from PHEs. So to resolve this issue, CSTEP, as you know, developed a differential pricing mechanism that would help PHES uptake in India and which would be presented during today's session. And we will hope to be able to discuss some of these issues and how pricing mechanisms can be used for making sure that more pumped hydro storage is used in the Indian grid. I must also take this opportunity to thank the support of Shakti Sustainable Energy Foundation, and we will get to hear more about that going forward. So, very warm welcome to all of you, and I'm really looking forward to today's discussion. I will now hand it over to Mr. Abhishek Nath, the Sector Head for Energy and Power at CSTEP. Thank you, everyone, and welcome.
Thank you, Jay. As Jay put it, the growth in the pumped hydro sector has been tepid, and it has not really been very fast. And of course, some of the reasons that we know are the high gestation period, the amount of capital it needs, and so on. But I think we need to discuss this a bit more, and that is what the session one is about. We'll be discussing the need for pumped hydro storage in the Indian grid, both from the perspective of balancing as well as being able to provide a clean storage system. So with me in the panel are Mr. Sumant Shankar Rao and Mr. Pankaj Batra. Sumant sir joined Karnataka Electricity Board in 1977 as an assistant executive engineer. He worked in various capacities in the field of operations, maintenance of distribution, testing and commissioning of substations, and large hydro generators up to 150 megawatt. He also worked in design and construction of substations and transmission lines. He was also involved in negotiation of PPAs and did system studies. Suman sir worked as MD of distribution in Karnataka, distribution companies in Karnataka, most notably the MESCOM, Mangalore Electricity Supply Company, and and as MD of various other companies like Transformer Manufacturing Company, Head of Engineering in the Transmission Company, and so on. He holds a degree in engineering, a degree in business administration and finance, and has also done uh, a course in relaying and protection at Roorkee. So welcome, Suman sir.
Thank you.
Welcome to I will also introduce Mr. Batra, though I don't really know whether he is joined. He'll be just about joining, but I'll introduce nonetheless. So that
I've joined Mr.
that's
Rath.
great. That's great. That's great. That's great. So Mr. Batra did his VTech in electrical engineering and diploma in systems management, diploma in financial management, and a diploma in public speaking. He is currently the project director of USAID's SARI EI program being implemented by RADE, which is a reputed think tank in Asia and deals in all aspects of promoting cross-border energy trading in South Asia. He was earlier the chairperson and CEO of Central Electricity Authority, Government of India, and he was responsible for overall development of Indian power system. He was a member planning of CA, dealing with various policy and planning functions in the power sector. At the ground level, he has worked in the Western Regional Lok Dispatch Center as system operator. He was responsible for operation and maintenance of powerhouse, switchyard, and dam in Chukha Hydropower Corporation in Bhutan, and later for the transmission and distribution system of Bhutan. He also worked as chief engineering in CERC, formulating various regulations. So welcome, sir. Now, as we are discussing the role of pumped hydro energy system in the Indian grid, and we have already raised one point, nevertheless, that there is only a tepid growth and not a very fast growth. So my question to you, Suman sir, and to Mr. Batra is, what opportunities do you see for pumped hydro storage in the Indian grid? And what policy interventions or initiatives specific to pumped hydro can be undertaken so that it emerges as a front runner? Mr. Batra, would you like to comment on that?
Sure. Uh, yeah. So when you have intermittent sources of energy like wind and solar, then having storage, energy storage is a boon, and not only a boon, it's almost a necessity. Although we would be able to manage if we have more flexible sources of generation like hydro and gas, and even with thermal, where they with some modifications you can have flexible thermal power plants. But it would be better if we have storage so that the coal-based plants or thermal plants do what they're best supposed to do, which is act as baseload plants. Energy storage would be a boon, and the oldest form of energy storage plants are the pump storage plants, which have been there for many years. In India, we have also about 4,500 plants which are in operation. However, not all of them are functioning as pump storage plants. Around 3,300 are now functioning as pump storage plants. Earlier it was 2,500, but they are operationalizing the non-operational ones slowly by slowly. So that is happening. And of course, there are a number of others which are under construction. Tehri pump storage plants of about 1,000 megawatts. Then you already have among this 3,300 Barulia power plant, which is pump storage. Now, what distinguishes Purulia from the other pump storage plants are that it is not river based. It is off river based. It's a closed loop plant, which means that you didn't have to do too much of resettlement and too much of work on that. So it's much cheaper. And it was only a stream which was flowing through from one natural reservoir to another, and they dammed up the natural reservoir at the bottom, so they built up water over there through water harvesting, which took about 3 years. So that's one side, but they're also going for a second one, which is Turga, where they're going to start construction. That one is of 1,000 megawatts. Purulia was of 900 megawatts, and they also have a phased plant number 3, Bandhu plant, which is again going to come up in the future. And Greenco is a renewable energy company. Greenco won the bid for providing renewable plus storage. So they have solar plus wind plus storage, and the storage they are using also is an off-river plant in Andhra. In Karnataka, I think. So these plants, the off-river pump storage plants, take almost half the time to build as compared to a river-based plant, and cost almost half that of river-based plant. So there's lots of sites which are there in India. We had done a study through the Australian National University and discovered there are thousands of sites in the Himalayas as well as in the south, which can be used. So that's a big boon. Of course, you have other forms of storage, which are battery storage, which are new and are developing, and the costs are coming down. But the other advantage of a pump storage plant is that it can store water over 3 hours, 4 hours, 5 hours, which battery becomes more expensive as you go for more and more hours of storage. And these pump storage plants, of course, have a very long life. They have a normal life, which is approved by the Central Electricity Regulatory Commission of 35 years, but they can go on to 70 years also if only the electromechanical equipment is renovated, maybe sometimes replaced to some extent. And so if you take the levelized tariff for using this as storage would reduce considerably if you extend the life through carrying out renovation and modernization. There are also 3 other plants which are under which were not operating as pumped storage plants, which is Sardar Sarovar, Kadana in Gujarat, and Panchet in DVC. So there's a lot of scope for pumped storage plants, especially the off-river ones. I believe the Ministry of Power will be coming out with a policy on pumped storage plants in the near future, which would give a boost. They've already come out with a policy for hydro plants, where a number it's been treated as a renewable, and a number of benefits have been given so as to reduce the cost of hydro plants. But a policy specifically on pump storage is on the cards, and probably it will come out in the near future. I think as a start, I'll say only this. Okay, Abhishek, right?
Thank you, Mr. Bhatha. Sumant sir, the same question to you, but perhaps from a slightly different perspective, because you have been in operations at various points of the energy system, but you have also been the MD of DISCOMs. So, what do you see from the DISCOM perspective? How do you see the role of pumped hydro storage in the grid?
Technically, let me say that from the operations point of view, I was on the transmission side as well as the distribution side. The use of a pumped storage plant is definitely necessary in the Indian conditions when the policy of the government, which is also good, that from the global warming perspective, that they're going in for 450 gigawatts of NCE plants, wherein the solar, they have got a 60% or 70% of solar is going to come. However, when these plants have to come, what is the capacity of these plants, and even at every location, what is the size of these generators should be very carefully chosen. What I'm trying to say is that today, you take Karnataka's peak load, post-corona, which was the pre-corona was also around 12,000. Now it has almost reached 12,000, 12,500 megawatts. The Karnataka represents 8 to 9% of the electricity consumption of the entire country, right? And the peak requirement in southern and northern grids are at different times. Now, with this in condition, now a pumped storage plant is almost like a hydroelectric plant, just that it has got one more pumping feature. So it requires a lot of environmental clearances, and the gestation period of these projects are long. So therefore, whatever the cost effectiveness we project in the DPRs will definitely escalate, and to control that, one best method is that you have to plan very well, meticulously, all that, okay, and then the construction portion has to be strictly adhered to the schedules. Otherwise, your the cost that you have projected will go for a toss, which is what has happened in the Tariff project. Now, the second point is that instead of having a very large power plant, you have to very carefully design. In my opinion, for example, a grid of 12,000 megawatts and with a growth rate of 7% per annum in Karnataka. Well, okay, I feel that a pumped storage plant of the capacity of 1,500 megawatts may be sufficient initially. However, this has to be distributed at different places. It is not that it need not be thought of as a very big plant at one place, where you will land up in a lot of other issues of evacuation, or the evacuation issues, or even the environmental issues, which is the biggest one I foresee. So what can be done? It can be 400, 500, 300 megawatts at different places, right? And even each plant can be sized of 100 megawatts of units, so that it can be started as a pump, or it can be used as a generator, and the construction time can also be squeezed. Added to this, now in certain states, some of the thermal plants which are running are outdated, right? Now they are all of 20 years, 15 years, 25 years old machines are running, and they have to be eased out. I'm telling the coal plants. Okay. Now the present machines can operate almost like this. Like there is a flexibility of operation of about 35%. Supposing if there is a 200 megawatts unit is there, it can ramp down and ramp up in very fast time at 35%. Such state-of-the-art machines are available. Now, definitely, it is not a replacement for pumped storage plant, but wherever you are removing these old machines, if such state-of-the-art machines come, you see, the transmission line is ready. Environmental clearances need not be obtained if you keep the generating capacity at the same level as the old generator. But except the advantage is that the ramping up and ramping down will be about 35% of what is the rated capacity. So After all, why do you require a pumped storage plant or a battery storage or anything? You require a ramping up and ramping down to keep the frequency and the stability of the grid. But this is not a total solution, but it is a cheaper option in the Indian conditions at the moment, wherever you are going in for replacement of these plants, right? And of course, the final solution is the pumped storage plant, and so you have to plan at what stage it should come, because the gestation period of all these NCE projects, especially solar, is very small. The gestation period of a pumped storage plant is as much as a hydro plant. So the timing when it should be operational, it should be very carefully planned, especially when it is more than 5 years. The governments will change, policies will change. So there should be a continuance of policy on these and the commissioning of these plants. This is what I want to summarize on the questions that you have raised. Now, when you go to the global perspective, see, it is the kind of money that you have. You can't compare the kind of resources the US has or the kind of resources China has with that. See, after see now, as on date, our installed capacity is 4,000, as Batra Sahib said, and then another 1,000 or 1,500 megawatts may come, and that is from the Indian conditions. That 5,000 megawatts of pump capacity is very, very small for the kind of planning of 450 gigawatts of NC that is going to come. And this 450 gigawatts, if it is going to come, it may come in next 5 years or 6 years, if it goes as per plan. But you can't build a matching, pumped storage plant within that time. So what is the solution? I said, when you are replacing an old thermal plant statewide, go for a state-of-the-art technology where a 35% ramping capacity is available. So so that will ease the life of, the life of the load dispatch operator will be made more simple. He will not be in tension in peak hours or while restricting the load. Of course, the planning of pump storage plant has to come. This is all I wanted to say.
Thank you so much, sir. I'll come back to 2 points that were raised while Mr. Batra was speaking and Suman sir was speaking. Mr. Batra, you pointed out that the levelized cost could be very low for pumped hydro plants. But one of the things that we actually did a study with support from Shakti Sustainable Energy Foundation, which tried to work out a case which we are going to present later today in the before the second session, and that is which tried to work out a case where a better pricing for the power output of the pumped hydro plants can lead to a better business case and can also lead to thus a higher investment in pumped hydro plants. Also, Suman sir talked about the gestation period of these plants being dry. Maybe we can go for smaller plants. So my next question is, I mean, based on your immense knowledge of various things, I'll first turn to Mr. Batra. Sir, what is the global perspective on pumped hydro, and what do we as a country stand to learn from interventions that have taken place elsewhere, especially on balancing the grid and making it more attractive to run a pumped hydro plant? Would you have some experiences to share on the global perspective?
Global perspective, there are a lot of pump storage plants, but I'm afraid I have not studied too much of global power plants for pump storage. But pump storage plants, you talked about the gestation period, which is right if it is a river-based pump storage plant. If it is an off-river based plant, it is lesser, as I said. So the second project of West Bengal, Turga, which is a 1,000 megawatt pump storage plant, they are saying that it will come within 5 or 6 years, which is much less than what a hydro plant, river-based hydro plants where you have to divert the river and things like that. That comes to about 9-10 years. Sometimes it gets delayed even beyond that if you have geological surprises. As far as the levelized tariff is concerned, it's the reason it's going to be low is it's going to be extended over a longer period of time because its life is much more. And the second thing is that, as I said, if you do renovation and modernization, you can almost double the life to 70 years. So because the civil works last for 100 years, so you don't have to do anything of the civil works. You have to do only work with the electromechanical parts. And civil works are normally the more expensive parts of a hydro project. What we require, it can be a style, if you, when you have, right now we are managing with because we've got 12% penetration in energy terms of renewables in India. But when we are planning for 20 and 30 and 40 and 50% of renewables in the long term, that's as you go on to that period, you will need more and more of storage. And I feel investing in pump storage after getting incentives of the government of India for hydro would be would make it worthwhile doing it. And of course, the CRCs come up with ancillary services, draft ancillary services regulations, which through competitive bidding, where anybody can take part. However, the incentives for anybody to put up ancillary services on a standalone basis are not so high in India because the incentives are pretty low. About 20% of the energy charge in one case, and in which is quite low, whereas internationally it is much higher. So as far as international prices for ancillary services are concerned, they're much higher. So maybe let's see when the final regulations come out. Maybe this is a start because we didn't have any competitive ancillary services up till now. When we do have this, then maybe it will encourage more players to come, and all technology agnostic storage will also compete because it allows not only generators, it allows storage, it also allows demand response to act as ancillary service. So I think there are a lot of opportunities which are going to come up in future, and the government having realized that either you curtail renewable power if you cannot ramp down to that extent, and what it indirectly does is, which we're not bringing it out clearly, is that right now if you are balancing from flexible coal-based resources, what you're doing is you're reducing the efficiency and increasing the emissions per unit of generation. So if you reduce the efficiency, then and underutilize that plant, so if you bring it down to 50%, then your fixed charges remain the same. So it's if instead of 80% you or 90% you bring it down to 50%, it's almost like doubling the fixed charge, which would otherwise come to maybe around, for a new plant, around 1 rupee 50 paisa per unit. It will double to 3 rupees per unit, fixed charge only. So there are, you have to look at it from that point of view. Also, our intention is to reduce emissions, and if you start using coal-based plants for ramping up and down, although it's since we have assets, we're doing it right now because that's more economical. But in the future, when you plan for the future, you plan for next 25-30 years. How to do that in the future? For the present, this is fine. Because they've already sunk money into these coal-based plants, and better to utilize it as per requirement. But there are a lot of other things. If you have storage plus renewable, then you also utilize the transmission system better, because otherwise for a solar power plant, if it's the evacuation system will use it only for 10 hours and 14 hours it will be idle. The evacuation from a solar park, say, to the grid, I mean that portion, not the entire grid, only that portion. But if you have solar with storage located coincident at the same place, then your utilization becomes much better. That's why the solar plants which are located in thermal power stations of NTPC, there's no extra transmission to be built because they're using the same transmission system in the premises of NTPC plants. So there are lots of that is second one. The third is the state. Presently the state is the control area, or they are subject to the deviation settlement mechanism, if which is a penalty if you exceed the deviation allowed in the cost the transmission, the connecting tie lines to other states. They have to bear it. But if they themselves have storage, then the deviation settlement penalty will get reduced, and if they have sufficient, it will not come at all. So there are actually 5-6 points which will where we are losing if we start if we do not have storage, and storage at the place at the location, or putting up renewable plants at the location of the storage, it's even better because you utilize the transmission system much better. Also, there's another thing I just like to, since you're talking about pump storage plants, I also wanted to point out that the new type of pump storage plants which are coming, the one which is coming up in Tehri, is a variable speed machine, so which is more efficient than a constant speed machine which was there up till now. And it also helps manages the frequency control much better, because you can pump water to different extents. It's not a constant pump, constant speed pump which pumps out at a constant rate. You can change the speed of pumping, so you can you can fine tune. You can get the frequency much better. And the one in the next one in Turga, which West Bengal is planning, also out of 4 machines, 2 machines are planned to be variable speed machines. This is a very good step India has taken, because very few countries in the world which have that. Switzerland is one, and Germany is probably another. So I think we are going in the right direction. We are becoming more efficient. We're going for the latest technology, ones which will help us control the frequency much better. So I think it's good to use pump storage, the latest technology in pump storage plants. Yeah, thank you.
Thank you, Mr. Batra. That you explained that very comprehensively, and I think we stand to gain from better technologies in this area. Mr. Rao, just one small question to you before we wind this up. You talked about the small sizes of power plants, and as Mr. Batra also pointed out, that if you are not running the plant to its full capacity, you are actually doubling its fixed costs. So, do you see any development happening in this area in either in southern India or rest of the parts of India, because you have a vast knowledge of the past scenario, especially in the southern India. So, do you see any small plants coming up now in this area?
No, no. See, when I said small plants, I specifically refers to the small capacity of the pumped storage plants.
Yeah.
That I said from the point of view of faster gestation. See, instead of having it at one location, 1,000 or 2,000 megawatts or 3,000 megawatts pumped storage plant, the generators coming in phases. If you have, if you start 4 or 5, I mean, if that should be available naturally. It is not that you can just think of putting 100 here, distribute 200 there. If such small capacity plants are put, finally you are pumping to the grid. You start the projects at 4 or 5 places if feasible, and the gestation you will be able to control. The cost you will be able to control. The environment aspects also can be controlled, and sum total you will be achieving this. Also, when I said with reference to the pump storage plant, instead of having, say, let us say, if 1,000 megawatts capacity is there, let us say the designed capacity, instead of having 4 of 250 megawatts, have 100 megawatts. So that will be a better utilization. That is the point I wanted to make. And the other question is whether in Karnataka, yes, they are going in for a 2,000 megawatts pumped storage plant in the Sharavati basins. Studies are going on, some evacuation problems are there, and I think they have submitted to CEA. I don't know the latest status.
Thank you, Mr. Rao. There is a question from the audience. Since off-river pumped storage plants have low environmental impact compared to traditional river-based pump storage plants, will it also lead to lower gestation periods in terms of lowering the total effort related to the environment clearance, Mr. Batra?
As far as environmental clearance is concerned, I think it will be faster because it doesn't displace people and it doesn't submerge forests and all. They're natural reservoirs which are there in the which are carved out, except that they don't have water. It's only a stream of water flowing which actually passes down then further. So my guess is the environmental clearance would be much faster. I'm not. I mean, since I'm not involved in giving the environmental clearance. I'm guessing that because it doesn't involve submergence, which is a big cause for seeing, from the environment point of view. So it's already a reservoir which is empty, or it's got very little water which actually is flowing through. So you just dam up a little bit so as to store the water. And of course, this gestation period, as I said, is almost half that of river-based pump storage plants.
Mr. Batra, this one last question from my side to Mr. Batra as well as to Mr. Sumant sir. There are large number of mining sites where mines have been dug and that area has now been lying vacant. How do you see the potential of developing these mining sites as pumped hydro plants? Just in very short, because we are coming to the close. So what is your perspective on that?
You want me to go first?
Yeah, sure.
I don't have much idea on that. I think Ms. Batra can speak.
Okay, so for pump storage, you require 2 reservoirs with a difference in height. So I guess the mining, I'm not sure how the topology of these coal mines are. I think it's one flat thing, so I don't think there is a difference in height between the 2 reservoirs. But if there is, yes, that could be considered. I'm not sure. So I think it depends entirely on the topology. You have to have 2 reservoirs with the head difference between the 2. Because if you don't, then there is no pump storage.
To my knowledge, no such planning in India.
Okay.
Correct me if I'm wrong.
No. We are gaining from your knowledge, so nothing to say there. So thank you, Mr. Batra, and thank you, Sumant sir, for joining us for this session. We actually had asked just 2 questions, but we sort of ate into the time of the Q&A also. But nevertheless, it was very informative. Now I'll request Manu Vodgal to take over and conduct the session 2, which is about pricing mechanism of the pumped hydro storage. And as Manu will talk about also again, this concerns the specific study that C-STEP did in this area along with support from Shakti. So over to you, Manu.
A very good evening to all of you. Today's session, I think, till now has been more towards the operational aspects of pumped hydro energy storage systems and the way it has evolved in the Indian context. But I think now is the work which CSTEP has recently concluded, which is a study on pumped hydro storage and also their recommendation in terms of pricing mechanism which they have analyzed and researched. I will now invite Dr. Amu Susanna Jacob to please deliver her presentation on this.
So I will just take through CSTEP's recently concluded study on the pricing mechanism of pumped hydro storage in India. So this was a project which was funded by Shakti Sustainable Energy Foundation. So we did discuss in the previous session also India has high renewable energy targets. India plans to install around 450 gigawatt of renewables by 2030. So with such high penetration of renewables, we will definitely require energy storage to match the supply and demand. And there are different types of energy storage technologies like battery, pumped hydro, compressed air, hydrogen storage, etc. So out of that, pumped hydro storage is a mature energy storage technology as well as it is available within our country. And it is a technology which has two reservoir system and which uses water potential energy. It has an upper reservoir and a lower reservoir. And when there is excess energy which is available in the grid, the water from the lower reservoir is pumped up to the upper reservoir. And when grid needs energy, water is pumped back from the upper reservoir to the lower reservoir, producing energy to the grid. So this is the storage technology which has the highest global installed capacity, highest installed capacity globally, with China having the highest out of that, like out of 169 gigawatt, 21% of pumped storage is found in China, followed by Japan. India has around the fifth largest PHES capacity. So we know PHES absorbs energy as well as releases energy, and hence it has different roles. So it can be used as a peaking power plant. Then it can be used for energy arbitrage, like selling energy when price is high and buying energy when price is low. It can be used as a load following asset. When used with renewable energy, it can provide round the clock support. Depending upon the reservoir capacity, it can be used as a seasonal storage. It can manage the seasonal fluctuations of RE as well as the load. It can provide voltage support, frequency support, and it can cater to the intermittency of the renewable energy. So when we look into the status of the pumped hydro storage in India, what we find that India CE has estimated around 96.5 gigawatt of pumped storage in India, out of which only 3.3 gigawatt is operational and 1.48 gigawatt is non-operational due to various reasons, and around 1.58 gigawatt is under construction. So out of the 96.5 gigawatt PHES potential, we have only 3.3 gigawatt operational PHES. So the pace of the development of PHES is very slow. So this is due to different reasons like the long gestation period, the environmental clearances issues, which we actually discussed in the first session, and also due to the low recovery from the current tariff system. And our current tariff system is basically a two-part tariff, which is comprising of the fixed and the variable cost. And our current tariff system is based on the amount of energy generation from PHES. It doesn't take into account the multifunctional role that PHES can offer. So the grid flexibility, what PHES can offer, it doesn't take into account. And some of the PHES in India, like the Gadgar plant in Maharashtra, they are operated usually as a no loss, no profit model also. So which brings to the objective of our study, which was basically to develop a pricing mechanism for PHES in India with high penetration of renewables and with special focus so as the revenue can be generated from the variable cost. And we intended to develop this mechanism for specific use cases. So for the study purpose, we developed it for two particular use cases, that is the peaking operation and the renewable energy smoothing. So before going into the details of the study, I thought I'll just show the tariff of different couple of PHEs in India. So I've divided the table into three particular banks: the existing ones, the Srisailam, Gadkar, Kadampari, Purulia plants, which are existing PHEs operating, the under construction plants, and the proposed plants. So we see that the average levelized tariff is basically in the order of 6 to 7 rupees. So for existing under construction as well as for proposed plans. So it's on slightly on the higher side. Now, so hence coming to our tariff computation methodology. So the first methodology is being developed for peak load shaving. So specifically, this methodology could be also adopted when PHES is being utilized as an energy arbitrage asset or a load following asset. And PHES here is operated in the market, the power market of India, that is the IEX market or the power exchange market of India. So for this analysis, we collected inputs such as short-term market prices, the market buy and the sell volume, then the load profiles, and also the details of the PHES operation. The dispatch strategy, we did two types of dispatch strategy. One is charging during low prices and discharging during high prices, and the other one is charging during low prices and discharging during peak load. And the pricing mechanism is like when PHES is trading in the IEX market, the peak and the off peak, the pumping and the generation prices are based on the market clearing prices of the market, and then we compute the profit. So we are trying to illustrate that particular methodology for a case study in Uttarakhand. So here in this particular case study, the PHES is operating in the market as merchant power plants, and we imposed one constraint in the analysis, that the buying happens when only if selling is supposed to happen. So you can see the graph here. This is a snapshot of the IEX market of the N2 region, which Uttarakhand is a part of. And the price minute curve, the buy volume and the sell volume is also shown, as well as along with the load. So the price minute curve for the year 2020 and the load for 2020 is overlaid and shown here. And for the analysis, we actually took the point of connection charges, both injection and withdrawal charges, as well as the losses was considered, and the IEX fee was also considered. Now, Uttarakhand, for the state of Uttarakhand, there is one proposed PHES plant, Tehri PHES plant, which is under construction. It is supposed to be completed maybe by the next year. So it has a rating of around 1000 megawatt with an efficiency of around 80%. So the pumping hours, so the buying time period in the IEX market for this particular PHES will be 7 hours. That's 28 time blocks, and the generation hours is 4 hours, which is 16 time blocks in the IEX market. So the generation consumption, we are actually showing it here. So, two particular dispatch strategy, as I said earlier. So one is the maximizing the profit or the energy arbitrage scenario. So you can see the pumping or buying from IEX market usually happens during the low price periods, which is the orange portion in the graph. And the selling happens, or generation when PHES is generating, will be generated during the high priced periods. So through which I can actually calculate the pumping price and the generation price. So the pumping price is my off-peak price, so that will be around 2.15, and my generation price will be my peak average peak price, which will be 3.94. So when I try to do the next dispatch strategy, that means pumping during low price periods and generating during high load periods. So the only difference is the peak tariff comes, my generation price becomes a little lower. So from 3.94, it goes down to 3.82. So in both these cases, I get a profit from my daily operation in the market. I get a profit. In the first case, I get a profit of around 1.8. And the second case, I'm getting a profit of around 1.2 rupees per unit. Now, this was done for just a random day. Now, actually, we tried to do this analysis for entire 2 years, 2 different years, 2019 and 2020. So we come to know that some of the days, trading, it's not good for the PHES to trade in the market because the price variability is very low. So the no profit generation days for the year 2019 is around 21 days, and for 2020 is around 53 days. And the ratio of the average peak to off-peak price to generate profit is in the range of 1.33 to 1.35. And the profit that is being generated for the year with respect to the price minute curve of the year 2019, we get around a profit of 157 crores for the year 2019. And 2020, which was a COVID year, we get a profit of around 70 crores. So this particular profit could be used for my fixed cost recovery. So if this profit which has been generated from my variable cost, if used for fixed cost recovery, the percentage fixed cost recovery will be around 16% in 2019 and 7% in 2020. So the graph below actually shows the plot for the revenue for the years 2019 and 2020. Now this was trading utilizing PHES as a market asset. Now utilizing PHES as a grid asset, specifically when it has been integrated with a renewable energy plant and it has to provide round-the-clock support and RE smoothing. Here the inputs that needs to be collected are the load, the renewable generation profiles, and the inputs related to market incentives, as well as some of the details of the PHES operation. And the dispatch strategy here will be charging during peak RE production and discharging during low RE and a peak load and high price. So so here the pricing mechanism will be when PHES is trading in long-term market. That's like when we go for a PP and a bilateral trade with the ESCOMs, and the ESCOMs will be able to, through this pricing mechanism, will be meeting the RPO obligations. It will reduce RE curtailment as well as it can provide dispatchable power. So this also we try to illustrate with another case study of Pinnapuram pumped hydro plant in Andhra Pradesh. This is a co-located pumped hydro plant. Now this approach could be well utilized for a grid connected pumped hydro plant having renewable energy source being taken from somewhere else as well. Now so some details about Pinnapuram plant is Pinnapuram is a co-located plant with a solar. It has solar installation of around 2000 megawatt and a wind plant of around 400 megawatt along with a 1000 megawatt PHES. And its generation duration is around 8 hours and pumping duration when it is being pumped for 9.22 hours. So we actually collected the load and the renewable energy profiles. We took the Andhra Pradesh load as well as the renewable generation profile of that particular region with the given solar and the wind. And the load, since the entire Andhra Pradesh load, we had to bring it down as seen by the pumped hydro in Pinnapuram. So, and we did this, we did the dispatch strategy. That means charging or pumping during high renewable periods and low loads, and discharging. The pumped hydro was discharged during low renewables and high load. And we try to determine the pricing mechanism. So we feel the pumping price will be the renewable energy cost plus the interconnection charges, and the generation price will be the pumping cost plus certain incentives. Since this pumped hydro plant is reducing the curtailment of renewable energy curtailment, as well as it is providing grid flexibility incentives, like it is smoothing out the renewable fluctuations. So certain grid flexibility incentives needs to be provided. RE curtailment penalty, which is offered to RE plants, could be offered to this PHES plant. And also, since the ESCOMs are now trading with the PHES plant and they are meeting their RPO obligations, because there is some avoided cost with high priced purchase of thermal or gas. So that particular incentive could also be provided to the pumped hydro plant. And generation based incentives could also be given to the pumped hydro plants. So we tried we collected the different the penalty, the incentives that is being provided. So the RE curtailment penalty, which is being provided to the RE plants could be, so these are the different scenarios. The first table is are the different, there are different scenarios for RE curtailment. Based on that, certain compensation is given, and this compensation could be used for the PHES plant. Then we took, since the we are doing it for the case study of Pinnapuram, we took the Andhra Pradesh tariff order and find out the deviation for the high priced thermal and gas. So we did that, as well as the grid flexibility scenario. We included some of those grid flexibility scenarios which is being given to some of the plants, so that compensation could be used, and so as to construct certain scenarios for the pricing mechanism of Pinnapuram plant. So so the pumping cost will come in the range of 3 rupees to 4 rupees per unit, and the generation cost with these incentives, with this incentives, will be in the range of 3.37 to 8.41. So the profit is in the range of 0.37 to 4.41. Now, this was with respect to the variable cost based financing for PHES. Now, the profit that is earned again here could be used for fixed cost recovery. So these two methodology focused on the variable cost perspective. Now, we also looked into some of the financing mechanism around the world. So for the capital cost of PHES, we find most of the countries follow the standard investment of 70:30 debt to equity ratio. And India also follows the same for PHES. So China, the only difference is they give this generation-based incentive on the tariff of PHES. So this promote competition between different PHES systems. Then USA provides certain budgetary subsidy on fixed cost part. So they provide debt capital at very low interest, and the government partners with the PHES developers, and also they provide this viability gap funding so that the PHES can be made viable. Now, Australia is, even though they don't have that much of PHES installations, but Australia has an expense distribution business model where multiple collaborators are involved, and thus risk is actually reduced. So these are some of the financing mechanism that is being used around the world. So coming to our recommendation, so we recommend, based on our study, a differential pricing mechanism with different pumping and generation prices instead of having only generation based energy charges. The profit generation will be used for fixed cost recovery, and the pricing mechanism should be based on these specific use cases. So for these use cases of energy arbitrage or load following or peak load shaving, PHES can be operated in the market as merchant power plants. And specifically for the case study of Uttarakhand, that is the Tehri PHES, we find that the peak and the off-peak ratio is in the order of 1.33 to 1.35 times. The net profit for the year comes to be 157 crore for 2019 and 70 crores for 2020, through which a percentage fixed cost recovery could be done as 16 and 7% respectively. So this is when it is being used as an energy arbitrage asset, and when in market, if they are supposed to provide certain grid flexibility, their profit reduction happens, and hence certain incentives might need to be provided. Now, for round-the-clock support and RE use smoothing use case, PHES is utilized as a grid asset. So we feel that one or combination of these incentives need to be given. That is the compensation for avoiding RE curtailment, then the avoided cost from high-priced purchase of thermal or gas plants, the grid flexibility incentive similar to the ancillary plants are getting, and also a generation-based incentive could be given. So specifically for the case study, we saw that the profit is generating from 0.37 to 4.41. And this could be used for, fixed cost recovery. And the fixed cost recovery ranges from 10 to 122%. So if I have to do 100% recovery from this profit, then my price differential between my pumping and generation should be around 3.62 rupees per unit. And on the alternative funding mechanism, we'll have to follow an expense distribution model with multiple stakeholders that might reduce risk, and maybe utilize good topology open pit coal mines or even government owned lands, maybe a budgetary subsidy on viability gap funding, and similar to renewable plants which are getting foreign direct investment, similarly that could be utilized for pumped hydro project. So this was the team which actually worked. Yeah, and that's with the study. We will, because of the time, I guess I will give it to Manu, and then let's do the next panel discussion. Then we will take all the questions over chat. We'll be happy to take all the questions over chat on the study. Thank you. Over to you, Manu.
Thank you, Amu, for this very insightful presentation. I think the new point which was already presented is that it is viable in the case example which you just presented. And if I just get into the nitty gritties, we are talking about a 1 gigawatt system, which is a theory dam, which is able to have a profit variance of anywhere between 71 to 157 crore. Which, if I go back into just basics, like anywhere between 1 to 1.5 crore per megawatt, we are looking at a payback time of anywhere between 7 to 14 years, depending on the profit which you get in a given year. So I think with this small background, I will sort of invite the panel, and we have a very distinguished panel at that. We have Vibhuti Garg. She is an energy economist with a very vast experience in the area of energy pricing and subsidy reform. Welcome, Vibhuti. Then we have Mr. Raghu Ramu. He was previously the superintending engineer for KPCL based out of Bangalore, and has a very rich, more than I would say 36 years plus of experience in the area of hydroelectric power plants. Then we have Mr. Sushil Kumar Soni. He was till very recently the CEO of POSOCO and now is the advisor to POSOCO, and brings a very rich experience over 4 decades in the area of power system operations. With this, I will actually open the panel with an opening question, and maybe I will sort of begin with the fact that we are only as good as our own set of assumptions. So I think you have gone through the broad understanding of what C-step analysis is. And if the panel can throw the light into what they think is the going forward feasibility of proposing a mechanism like this in the Indian context, as well as I would say the underlying basis. So I think with this, I will invite Vibhuti for her initial comments.
Thanks, Manu. Am I audible?
Yes, you are.
Great. Firstly, great presentation, Amu. Really enjoyed the thorough analysis that has been undertaken by C-step. Very insightful and informative things that came out through this study. Coming on to the remarks, I would say that it kind of sets out the tone, or it kind of sets out the case that, based on this differential between peak and off-peak pricing, there is a profitability element. So clearly, if pumped hydro storage is able to use that kind of an arbitrage or any other storage solution, and not just the pumped hydro storage solution, any solution that is providing this flexibility to integrate with the intermittent renewable energy generation sources, there is definitely a case, and it should give investors, especially, as well as the developers, the confidence that they will earn revenues over the next, since when the capacity gets installed over the few years. But my only concern, or rather an issue that I would want to raise. So for example, this presentation laid out that the difference between peak and off-peak ratio based on the last 2 years, 2019 and 2020, was around 1.33 or 1.35. When we are suggesting such kind of a pricing mechanism, is this going to be a constant ratio for the entire 25-year period? I'm not too clear on that. Maybe some clarification would be appreciated. Or is it something that we are going to propose like the way we have it in the gas prices? We have a 6 months moving average, when we take into account whatever the differences between the peak and off-peak prices, and we keep having that as a basis for determining these prices for any storage solutions, or as I said, any flexible generation that plays that role. So if that kind of a moving average can be computed and that becomes the basis, and it doesn't remain kind of static for throughout the life of the pumped hydro storage, I think that would be good. Or else I would say, if we can have possibly through this study, as I said, we have established the case that the difference between off-peak and peak kind of provides an arbitrage, as well as the for any flexible sources of generation. So having maybe a more simplified thing, which is very similar to what is being proposed, at time of day prices for both producers and consumers alike, which gives the kind of the right price signals for setting up capacity to meet peak demand or provide flexible supply to meet the grid stability. So a TOD pricing mechanism will essentially do the same thing, differentiating between peak and off-peak power supply, but it will be more dynamic and not static, which at any point, will represent the current conditions. And I would say, therefore, avoid any cancellation or renegotiation of tariffs between the discoms and the developers. We have been seeing at times, if you enter into any long-term PPA tariff, which is higher at this stage, but a few years down the line, the peak tariff versus off-peak tariff, that margin gets reduced, and then Discom suddenly again becoming very reluctant to continue with those PPAs. I think having that kind of a dynamic tariff, which kind of reflects that current condition, could really address this whole issue. So yeah, these are some of my initial remarks when I looked at the methodology, and I think there is a way to address that as well.
Thank you, Vibhuti. I think you're very insightful on that. Mr. Soni?
Excellent analysis. I will pose very head-on questions. All of us know that pump storage is required. Technically, it is good for the system, but it is not getting built. Why is it not getting built? Let's look at those. So the first thing is that the per unit mindset, volumetric tariffs, one has to go away from. If you look at it only as, and I hope I am audible. Yeah. So
look at my end, Mr. Soni.
Yeah.
There's some disturbance. Maybe if you can remove your earphones, that might help.
Actually, suddenly my laptop has started doing routine formatting, so it's making a humming noise. I can understand that. I will listen to it. So the issue is that we need to move away from volumetric tariff. How do we go about it? Just think of transmission. If transmission was to be paisa per unit, could we have built such a large grid? We could not have built. India has the strength of an all India grid, massive transmission. There are mechanisms to recover it. There is an O&M expenses also. There is a loss also. Everything that we think of pump storage exactly in the same way. As far as 20% loss, return trip efficiency is concerned, that can be handled through market, through stack of revenue, be it ancillary, black start, and name it and all. But as far as the fixed charge is concerned, I don't think that any of these calculations would foot the bill of fixed charge. Maximum number shown was 6%, 7 or 10% or 17%, but certainly not. So nobody would finance it, nobody will close it. So My simple suggestion is few, may not be very backed up by a lot of calculation models, but this is the gut feeling which I get out of my long experience of governance and the pricing and the competition. Number one, think of pump storage only as shared project. No one state should go for one pump storage. It is very difficult. The risk hedging will take place the moment you have gone for a shared pump storage. That's the first. Second point I have is fixed charges of pump storage must be bid out. Of course, the cost plus is not the bad word. So the total fixed charges should be recovered as if it is from the transmission pool kind of a thing. Let people do PPA whatever they want to do. The balance should be recovered from the pool. After you have taken care of the fixed charges, I will come to the nuances of it. After you have taken care of the fixed charges, then comes how to optimally use it, how to use it for energy arbitrage or ancillary and so many things. That you leave it to the system operator. Provide them enough of the mechanism, which already we have now enough of mechanism. And if some excess revenue is generated out of that, let it offset some of the fixed. That's something which is workable. Our strength is that we have an all India grid. If you want to utilize the pump storage for the grid as a whole, it will be much more efficient. One need not worry about a state's profile and things like that. States still can have a PPA. They will have the first right. But if they don't use it, let it go into the all India and so the 20% loss of return trip is taken care of. It will generate some profit. As far as the sunk investment is concerned, let it become par as it common kitty. We have transmission. Imagine if transmission was to be built as paisa per unit. It would have been impossible for lines which are utilized hardly for 20% of time. But we have hundreds of sensitive lines and they are working. So pump storage has to be thought in a completely different fashion. So this was one part. Second was, how do we know which pump storage to take? And I agree with Suman that we should have small ones spread across the country. So how much pump storage is required in which time frame? Nobody else can do this better than CE. Individual state-wise assessment of it would be absolutely sound. Should be done on an optimal capacity expansion for which CA is the right organization. They have the visibility of all India wise aggregation. So they come out with that this much of pump storage is required. CA Hydro knows about the candidate plants which could include off-river pump storage, converting the existing ones quickly, or which is easily doable, which will have less R&R issues. These are all again, and create DPRs and keep them ready. These jobs have to be done by a centralized planner. Market is no substitute to planner. Planner is an arm of the government which has to function. Once these two things are done, then the way you bid out solar, you bid out this pump storage also. And the bidder is, the service provider is assured of fixed charges through the sword of the king, the regulation, the fixed charges will be paid. Now you perform with all the performance. I think this is something which is doable. Second option which comes also addition which comes to my mind is that in the adequacy statement of every distribution utility, there should be some component to show whether how is he able to handle. So, so maybe that an utility has to demonstrate that he has 3% or 4% of pumping capacity also. This is in just what I wanted to say, and then subsequently, as and when required, we can get into it. But simple arbitrage, even if 1.3% or 1.4%, we have done huge calculations. There is a hydro report on Kosoko's website. And we have seen how we can optimize. Even if you optimize maximum, you cannot meet fixed cost of the PHES. And that's where the trick lies. How do we ensure recovery of this? Thank you.
Sure. Thank you. I think the point you made very strongly is the fact that markets can have no substitute for planning. And I think that is the byline, I think, which you are standing by. With this, I'll invite Mr. Raghu Ramu for his comments.
Hello, everyone. I'm audible, I suppose.
Yes, you're audible.
We are discussing about the pump hydro plants in particular with respect to its viability and its capability to meet the requirements of the grid in a changing scenario. Now, 5 years back, perhaps we would have been talking about the need, where we bring the power and other things. Now we are gone after the 2015 summit in Paris. We are discussing now what might be achieved to determining how to meet the collective goals for a sustainable energy system. We are no longer discussing what to do, we are discussing how to do it. And there are specific energy storage solutions available to meet this new technology and new goal-oriented decarbonizing the energy sector. Items being added as and when new targets are being fixed. We saw there's a exponential growth and target fixed for the renewable energy sector from starting from a mere 20,000 megawatt during 2010. None after 2015 summit we gone up to 175 gigawatt. Now 2030 we have 400 plus. Now this has changed the energy mix in the system. We purposefully we are going. We talking about 40% from renewable energy by 2030 to meet our international obligations. Now this has opened up number of challenges to the grid operator. It has introduced uncertainty and variability, but we require reliability and security. There are a number of technical solutions available, maybe with different technologies, but of course pumped hydro storage stands in front of us in a big way. You just saw the presentation that 3 major countries, China and Japan and USA, hold about 50% of the complete hydro pump storage capacity in 3 countries. One more thing we have to see in these 3 countries also, most of the plants are very old. Most of the plants are very old, and capacity addition even in the pumped hydro stations in these countries have not happened recently. Whatever the existing plants they have are quite old. The example in US itself, there are 45 plants, out of 45 plants of nearly 30 years plus duration, which are in operation. This is much this much has power has come from US market when there was no capacity addition what we are talking about now in the renewable energy sector. So requirement of a pump storage system as a grid element is found necessary even earlier, but it was not put into practice in Indian market because of the shortages we were facing in the total energy requirement itself. Now, from 2018 onwards, there is a noticeable change. The availability of energy is almost meeting the requirement, and we have new players, new systems coming into the picture in terms of renewable energy. The lot of thermal addition we did during 11th and 12th plan did serve the purpose on that day. Now, because of this renewable energy, we are running at 50 or 60% PLF right now. It has added another element to the problem of the system. Now, whether we like it or not, we have to change. We like it or not, we have to change. This is going to happen. This is going to happen. Because the trends, when the target was fixed at 175 gigawatt, many were not very sure. But now the target of 2030, nobody is having the doubt about that. Two may not be out of place here to mention that two big industrial houses have shown interest in setting up the plant for solar under Atmanirbhar scheme. Points out that. Now, how to recover? Definitely, any investor, whether it is state or a private person, would like to recover the cost of the equipment and made the a decent profit, if not no. Now, it is a energy sector is in India. Both central and state government are doing it, and it is necessary for any developer, whether state or central or the IPP, to have a fixed assurance of running the unit after having made the investment. There is no doubt about the requirement of the pumped hydro storage in the system. There is no doubt for any person for the requirement of a system, but now how to make it cost effective and whether it compares with any other technologies which are coming. When we did it in Kolar in Karnataka in 2010, we spent for a 3 megawatt station, we spent 75 crores, and prices now is comparable with any other normal this thing. So initially the solar power was also provided with viability gap funding. KPCL has also executed few projects under viability gap funding. Now, nobody talks about the viability gap funding for the solar. Now, we have come to a stage where there is a requirement for the pump storage. Definitely, it is a cost intensive. We require capital cost more and gestation period about 5 to 7 years. Depending upon the project location, it can be lower or higher. That depends upon the project location. Now, how to recover the cost? How to recover the capital cost? Now, for this, we have to see the role, whatever the tariff fixed by the central government authorities through earlier by the government and now through the regulation by regulatory authorities and the tariff policy over a period of time, they have recognized the importance of hydro station, and during 2014 itself, they have provided a 1% incentive on rate of return for the hydro stations, which is also available for the peaking station, for the peaking hours, peaking support they give. This is also available to the pump storage. This only shows that they are aware of to give the incentive for the specific purpose. Where earlier the Sharavati generating station in Karnataka was doing the energy, meeting the energy needs of the system. Now it is a peaking station because of the addition of thermal and other projects. So similarly, the changing role of the hydro in general has been recognized, and initial beginning was made providing the rate of return a 1% increase in that. Now with this coming into picture, they have seen the there is a capital cost involved more here compared to any other type of technology or the projects. we have. Now, CA has taken number of steps, CA in general and regulators and the government have taken number of steps to reduce the cost. They have increased recently from the
Mr.
from
Raghu,
25 to 40. Yeah, 25
Raghu,
to 40. Yeah.
Yeah, what I was saying is that probably it would be useful if you can share more of your thoughts over the question and answer, because I'm sure many of these will overlap there.
Yeah.
I will also invite questions via the chat box.
Yeah.
And while we are there, I think let me also pose a few of the questions which I think our panelists have already sort of identified. I think, Vibhuti, you mentioned there is a reluctance of the DISCOMs to enter into PPAs, right? So,
one of the suggestions made, it is also there in the draft guidelines published for the ancillary services by the government, that it should be treated as a grid element. It should be treated as a grid element, whether it is done by a state or from a central system or from a IPP. Another thing is what, like we said, the China was doing. What China was doing is the cost sharing mechanism, that is electricity capacity and the pumping loss shall be included in the allowable T&D cost of the regional power grids, which is further transmitted to the provincial power grids. This is what being done in China, whereas in Australia, it is a distributed mechanism where number of stakeholders have a stake in this pump storage system. Even though it is a very well established market is there in US, they have gone for a viability gap funding. There is a support for the capital cost. Government of India in the NEP 18 has also noted the need for central assistance or the subsidy to all these plants. In its recommendations, it is also stated that infrastructure cost not to be included in the total cost. It has also stated that incentive for power generation during the period of off-peak period, that is, off-peak period we consume, we are a consumer. Incentive should be there not only for generation, for the consumption during the off-peak period. And most important is differential tariff for peak and off-peak period.
Okay, thank you so much for your comments there. I will also invite the other panelists to give their observations. In fact, I've also received a question here which says that when are the hydro storage plants that were studied expected to achieve break-even? Were they planned for peak hour service or RE curtailment? The second question is, what is the significance of ternary set PHES technology, which means separate turbine and pump with common reversible motor and generator? Is it a viable option for new plants in India? And how can we make time of day tariff feasible? Will other consumers in India allow? So this is another of the questions. But I think fundamentally, I think the question is, can markets be a substitute to planning? Which I think Mr. Soni, you really sort of pointed out. And that's where you had a concern, Vibhuti, as well in terms of the ratio and the assumptions which sort of they come in. Now, can I see some comments from both of you on surrounding any of these questions, or maybe the assumptions, maybe in due reflection, you sort of rethought your answers or you've arrived at some other inputs based on maybe, for example, Mr. Raghuramu's input as well? Vibhuti?
Sure. I think Mr. Soni highlighted a very, very critical issue that, while just having a differential pricing mechanism can address a part of the problem, and it enables profitability while it only enables recovery of fixed costs to an extent. So clearly we need other mechanisms in place apart from this differential pricing mechanism to recover fixed costs, because unless there is confidence by the investor as well as the developer to recover the fixed costs, they will not put any money and into establishing or deploying these pumped hydro storage systems. So one of the other things which again has also highlighted, that if the government, like the way we did it for renewables, any expensive technology can be supported through government, either through viability gap funding scheme or availability of finance at reasonable rates. So we need those kind of other support mechanisms also in place in order for these solutions or these technologies to become more commercially viable. So it has to be a combination of these regulatory mechanisms as well as support from the government as well as the planners in getting these projects more commercially viable and understanding of where it needs to be located. So yeah, I think it has to be more of both and not just one.
Okay, so one size cannot fit all. That's the proposal you have.
Exactly.
So, Mr. Soni, I mean, you laid a very interesting thought that we can borrow a leaf from the way the transmission system has been able to very successfully ramp itself up over the last 2 decades. So, what are the next steps you would like to propose to really make pumped hydro a viable option going forward? Perhaps even better than battery storage systems, because they're also trying to borrow similar or something on similar lines.
So, cutting the long story short, if I was to build a merchant transmission line, we discussed all these things for decades in 80s and 90s. We could not have built any merchant transmission. The way there was a policy pronouncement from the rooftop, 175, nobody questioned it, and now everything is falling in place. We need a very loud and clear policy pronouncement that we need pumped. And how would policymakers do it? It has to be backed up by study at CA level. They got to bite the bullet and say that yes, we need so much, which they have done also in their optimal capacity. That's up to that is perfectly understandable. It is clear. Now coming to recovery, these all small things, 1% infrastructure first will be built here, some financing will do, VGF will give, some. All these things can be, add-ons, but fixed cost of pump storage cannot be recovered by any other method to my limited understanding. And we got to bite the bullet and say that the way we build transmission, we would have a regulated one. And the last 1% of the load of any utility. If you have a load duration curve, what is the cost of that last 1% load which we try to meet? Let's say 200 gigawatt all India is. The last 1%, last 2000 megawatt would be lasting hardly for some percent of the time. And for that, if we keep on adding our other capacities, it is absolutely not correct. We've got to move to demand response. We need to have storage. And as everybody said, Kadamparai we were not able to run. We were running Sharavati as a flat energy, but now it's doing peaking. So things have changed. We have come out of the shortages. We have now adequacy. So the adequacy statement demanded by the regulator has to have all these details. That show me your load duration curve, show me how much flexible generation you have, show me why you will not be able to meet that 1%. Like that, there are a lot of other things to do. Then what will happen is that they will have a requirement of, let's say, 35 megawatt of pumps. Now, 35 megawatt pump storage, everybody cannot construct. So then you have a shared project at all India level where everybody can satisfy his requirement of that much component in his resource adequacy statement, and then a shared project is built And now we have systems and procedures in place that even it can be used as ancillary services, it can be used in arbitrage, economic dispatch, and name it. Everything can be used. So those are all settled issues. The main issue is how to construct a plan, how to assure fixed charges. And none of these small methods here and there will work. Yeah, you need a big hammer, a big policy. Yes, we will have 2,000 megawatt of pump storage. These are the pump storage sites. We will bid it out, and their fixed charges will be assured to the pool. The regulator has to decide how we will do it. That's it. That's the only way, practical. And India has shown how we have built transmission, and other countries are struggling with transmission. They are not able to do transmission exactly like all these, finer nuances. So this is, to me, it appeared, and we are discussing this a lot of models. The IHA, International Hydro Association, is regularly holding the meetings. So we have seen the frustration in this whole thing. Even I would go one step further. We have a vision of one sun, one world, one grid. How about having a pump storage, large pump storage, maybe in the mountainous countries like Nepal and Bhutan, where all the countries can have their shared resources. Shared resources, hedge the risk, assure the developer, and a lot of advantages are there. So I would say that we should have large also PSP besides small PSP of off-river kind, which has not been happening for quite some time, other than Purulia and Turga, which was mentioned. So CA has to really move. They are the planners. They must say that the country will need how many pump storage, which are the basket of pump storage whose DPR is ready, more or less clearances have been obtained. Now bid out. Then things will move into motion. I'm cutting the long story short because the rest all other things are known to all of us. Where do we differ with this, and what could be the key issue which has to be handled?
Got your point. I think very well said. I'll come to Mr. Raghuramo. So you did talk about the international experience which is available for all of us. And in the context of that international experience, I mean, how do you see pumped hydro? Of course, I think there is a long gestation time. So the basic question is, how do you really plan, say the state of Karnataka, the kind of storage needs which you have, and then activate them going forward?
Yeah, traditionally we are thinking, the moment we think a large hydro, we think about building a huge dam, and it will bring in associated problems, maybe much more than when we did Sharavati 60 years back. Now, there is a necessity to change our thinking. If one visits the Purulia pump storage plant, somebody also mentioned it earlier. See, it is not a site which normally they would have housed the hydro power plant more so. Now that site has been developed. What is the water capacity required? It is hardly 0.5 TMC, and there was no submersion. Because of that, even our small ponds have much more water capacity required for that. The 1000 megawatt Purulia pump storage scheme has got a storage capacity, upper dam storage capacity of 0.5 TMC and 0.4 TMC in the downstream site. So this will reduce, such sites are available in different parts of the world and in different places in Karnataka also. This is to be identified and taken up. There are other plants like Sharavati, which has got both upstream and downstream reservoir already ready, available. Those things should be made use of. No new construction of dams. Those things will be, those things will be sufficient to reduce the time.
Mr. Raghuramo, I've just received a question, which I think you are best poised to answer this. how much is it technically and financially feasible to use existing hydropower plants to convert into PHES plants? A quick yes or no. Do you think it's much more feasible
Yeah,
rather than?
it is site specific. It is not possible in every site. We have a system of integrated operation of the river. We should have an integrated operation of. We have got 2-3 powerhouses, one downstream of the other. So there we have already have a upper reservoir and upper reservoir of a another plant, which can be used as a lower reservoir. So when already 2 reservoirs are there, when we do the integrated operation of the river, we have the 2 reservoirs available. Those stations, those sites can be used for the conversion of the pumped hydro scheme. Sharavati is one example. There are similar many projects like that in Karnataka where it is feasible to do it.
I think we'll have to, good things come to an end. And I think I'll have to call it an end to today's discussion as well, though one could have sort of gone on for at least the next 10-15 minutes. But any last points which you may have, the other panelists like Ruti, Mr. Suni? Okay, then I will hand it to Abhishek, who will help us with the next steps for today's session.
Thank you, Manu. Yes, all good things come to an end. So, but that this is actually a very discussion, and I think this can set the tone for next. I mean, taking forward this discussion and trying to push for this agenda of having more PHES, especially in the balancing role. So I would like to thank here again everyone who has been a part of this webinar. Jay for welcoming us all the participants and the panelists. Then for the first session, I'll thank Mr. Batra and Mr. Sumant Shankar Rao for insights in the PHES opportunities that lie in India, as well as for the perspectives on the various uses of PHES. Manu, who as the director in Shakti, who looks after the climate policy initiatives, has been very supportive of us in this work, especially along with Akansha and Saloni. And I thank you, Manu, today for this very able moderation of the session, especially on the pricing mechanism for the PHES. Amu has led this work and she made this presentation today very insightful. And though I have seen it a couple of times before, but I think she carries with her the excitement of work and she presents with a passion. Vibhuti pointed out something very, very important, and that is what is the long-term planning in terms of what rates do we see in the coming years for this kind of analysis that Amu had done, and how practical we can make it in terms of achieving the objective of meeting the fixed cost and getting a profit on the revenues. Mr. Suni, you pointed out something very important. Not only that planner is, I mean, markets are no substitute for the planner, but also that we have a great strength in the Indian grid. It has been built over the years. The transmission infrastructure could not have been built if we had looked at this per unit rate. And of course, we need to find innovative ways of trying to settle this fixed cost problem that most of these PHES plants have. Yes, I think a very important part though will be the policy push, which has to sort of, I mean, I don't know how, but possibly in the form of a diktat that we have to set up PHES plants, and then various arms of the electricity market will and the planners will have to sort of operationalize it. Mr. Raghuram pointed out very good things, especially about the viability gap funding. There was a point of time when solar plants did not were not being constructed without this viability gap funding, and today they are so easy and so quick to construct. So there are many. I mean, we have many takeaways from this session. And I think one of the important things is that I saw in the whole of the two sessions that we had a distinct desire to address this solution, and that coming from people of caliber as have been in this gathering. I think, and with the vast experience they have, both people who have been at very high levels in the government and people who are in think tanks or operationalizing things. So I think a unison in vision, and I think this will sort of encourage us to take this work forward, and we'll look forward to your support again in the future. Thank you all once again. Thank you, everyone.